Alright, let's answer question 14 and 15. So here are the necessary imports we need. And I'm going to use the coupling map from the transpiler package so that we can look at what coupling maps are. We're going to use our IBM free account to run a circuit on real hardware to see what the real hardware does for coupling maps. And question 14. Which code fragment snippet would execute a circuit given these parameters? So the first parameter is we need to measure the circuit 1024 times. Second, we need the chasm simulator. And third, the qubits need to be connected linearly. So we're going to make a coupling map. What is a coupling map? It's a map that specifies which way we can do CNOTs. So the real devices that we have today are limited by their physical behavior, their physical configuration. Right? The qubits are going to be formed in a lattice of sorts, where qubit 0 may be quite some distance away from qubit 5 that you would like for some reason to do a CNOT from. And so in order to make that happen, the quantum circuit would have to be transpiled because there's not a physical way to do a CNOT between those two qubits that are that far away. And so the physical limitations that we have today cause our circuits that we run to be limited. So, is option A, B, C, or D the right answer? Well, let's look at what the coupling map is for a certain backend. You can actually see it using the plot gate map function, and that will show you what coupling map the backend you give it is restricted to. So first, I'm going to filter the backends to make sure I don't have a simulator, because the simulators, since they just simulate a quantum computer using a classical computer, they don't have any coupling, because theoretically we should build a device that has no coupling. Any gate or any qubit can map to any qubit. That's the hope, but currently that is not realizable, and so the backends have coupling maps, but theoretical devices like simulators don't. So we want to make sure it's not a simulator, and if we plot the name, we can see, okay, Bogota's has this coupling map. So I said plot directed equals true so I could see if there was a specific edge, if one was connected to the other but not the way back. But here we see this is a two-way edge in and out. So the source to the destination of this directed graph says Q0, which is the 0 standing for Q0 on this node, is connected to Q1 and vice versa. We can do a CNOT between them. They're coupled together. See, Q1 is connected to Q2, Q2 to 3. So see, it's a linear map. It's kind of cool. Some of them also have Q1 to Q3. You'll see that. So it's not just, you don't just have to go online. But this means I can't do a CNOT from 0 to 4 and run it on this backend. It would be impossible. What happens is the Qiskit functions transpile it, which means we take the quantum circuit and we map it in a way that it can actually run on the desired backend. So when you call execute, it does a transpilation phase to convert your quantum circuit to one that actually can be run. And believe it or not, most quantum circuits, at least the ones I know of, can all be mapped to a physical device. So even if you'd want to do a CNOT between 0 and 4, or 0, 2, or 0, 3, it would map it in a way that you'd be able to do that through swaps and so forth. So that mapping function, though, for the transpilation is an NP-complete problem, meaning that it's very hard, very time-consuming. It's not an easy problem, not just like, okay, we do one function. Like, it's dependent on the size, and so the bigger your circuit is, the longer it will take. But we can see what connecting qubits linearly would be like. So we give it 0 to 1, 1 to 2. This is an adjacency list, meaning that Q0 has an edge towards Q1. Q1 goes towards Q2, and so forth, and not backwards. So this is the source, and this is the destination. Source and destination. So that's what the coupling should look like for the third criteria. And here we see there's the coupling map that we give as the third parameter, as the coupling map parameter for the execute function. So of course we could try each one of these and see which ones don't compile, and then those would be the wrong answers. But actually some of them compiled even though they're still not the right answer. So we'll look at that, why that is. So it looks like that one compiled, and the coupling map that's created looks like the one we thought we should have. So this already looks like the right answer, because this is a line. This is 1,024 shots that we required, and this is the chasm simulator. So yes, this is the right answer. What about B? So B gets the IBM Q. I've never seen that before. It actually doesn't compile because they had a syntax error calling the get backend function. Should have been an underscore. So this one works. So it seems like it could be an answer. Maybe this is multiple answers to the right one. But I've never noticed that keyword before. And if we actually want to see what happened when we say job, we can look at the job and see if that keyword was used. So I created a hypothetical quantum circuit here. It creates the maximally entangled state between 3 qubits, 0, 0, 0, or 1, right? That's what the Hadamard does, equal superposition. So this is 1, 1 would be a 1, and this would also be a 1. This should create the equal superposition between 0, 0, 0 plus 1, 1, 1. And if we look at the object stream for the job, it used shots, just like we expected. That's the right keyword. And so you won't see repeat anywhere in here. Now, if this execute function passes on the keywords to the configuration of the backend as well. So if the backend used it, then it would be meaningful, right? But actually, the AER backend for the chasm simulator doesn't use it. So this is going to get ignored. So this actually isn't the right answer. Now, just so you know, this is the default. And so it's still a technical right answer, but because it's the wrong syntax, you shouldn't be giving it an unknown keyword parameter. It's not the right answer. And we'll see in question 15 a warning saying it's not the right answer. So what would what if we ran this without coupling? So let's see, we're going to test this on real hardware. We're going to run it on Bogota like we saw. And here's the coupling map. Let's check how it is ran versus with a coupling map versus not specifying one and using the default. So I just queued this, and so it should be in my IBM Quantum dashboard. Let's refresh it. So here I see I've just ran it. And let's see what it did to the quantum circuit to transpile it. So right now it's in the queue and it's actually running it right now. Well, there's the Hadamard, because that's the Hadamard decomposed into the basis gates. Here's the CNOT, but then it does a lot more Hadamards, and looks like it does some sort of, not sure exactly what that does, but it will perform our quantum circuit as accurately as possible. We can see by what is measured when. We wanted to measure Q0, Q1, and Q2 in order. We can see from that Q0 was mapped to Q2, and Q1 was mapped to Q0, and Q2 was mapped to Q1. So quite interesting. It changed the qubits around there to be able to still satisfy the CNOTs. See, we don't see any from Q0 to Q2 CNOT like we had specified right here. We don't see that happening. And so that's the example of that transpilation NP-complete algorithm. It converted it to a quantum circuit that could be run and change the qubit orderings. So what if we ran it without a coupling map? So we could see what happened here if we wanted to. And we see most of the measurements are like we expected to be 0, 0, 0, 1, 1, 1. If we execute it without, that should queue it up soon. And I just ran that 1221. There it is. We see something very surprising. Whoa, there it is. It's actually a lot shorter than I expected. It only had to do a swap. This does the swap. These three C0s performs a swap. So then it swapped. It did a Hadamard on Q3 instead of Q1. And see, we saw, okay, Q0 is Q3. But then instead of doing the C0 from Q2 0 to Q2 like we wanted, it did a swap. So it swapped what happened for Q3 to Q2. So then Q2 now becomes basically Q3. Then this is kind of confusing. But basically Q3 now has become Q2. No, sorry. Q2 becomes now Q0. I don't know. Anyway, somehow it's opposite, so that way when we do the final C0 is as if we were doing it from Q0 to Q2. Really cool, huh? So we know option A is the right answer. D is not the right answer because it used shot instead of shots, even though of course it'll work. Actually it doesn't because the positional does not have a follow. I have a syntax error. So for option A, that's the right answer for question 14. What about question 15? So we have the same sort of setup except we're using basic AAR, and we want to use a custom coupling. So is that mode equals custom maybe? Well, we already saw from question 14 that we had a custom coupling map parameter that we could use. So let's see which one of these compiles well. That works. Looks like A is the right answer. And interesting, the basic AER gives warnings, unlike the other one that we're using. It tells us which parameters weren't used. It's not used by this backend. So we know that's not the right answer. And here we see again, device and mode are not parameters used by the backend. And for some reason we don't get the warning here, but mode's not used as a parameter. So option A is the right answer. So both for 14 and 15